in this lecture, we will finally prove the Penrose singularity theorem. We still need to finish with our preliminaries though, and in this lecture we will introduce the energy conditions on the matter and causal structure. Another part of the preliminaries is other trapped surfaces, which correspond to the spatial cross-sections of particular kind of null hypersurfaces. So, let us start. So, let us consider some two-dimensional space-like surface. So, it means that all of its, so space-like again means that all of its tangent vectors are space-like. So recall that in general, we can always define two null directions, which are orthogonal to all space-like directions. So therefore, there exist two null directions, two null vector fields starting from S, which are orthogonal to S. So since we have two null directions, we can then construct two different geodesic congruences, and therefore two different null hypersurfaces. And let's call the normals to them U1, U2. So U1, U2 are their generators. And if you lower the index, the covectors will be normals. Good. So physically, this would correspond to having ingoing and, so for example in Eddington-Finkelstein chart we had ingoing light coordinate and we had outgoing light coordinate. So basically this can be treated as the null hypersurface of ingoing and outgoing null rays. Well, at least in simple situations. So, good. And for every null hypersurface, we can of course define the expansion. So physically, we expect that if you take such space-like surface within the black hole region, that is behind the horizon, both of the expansions would be negative, because we expect that we know that all causal curves would focus on the central singularity, and therefore the area of the geodesic congruence shrinks. So that's why we are introducing the definition of a trapped surface. A trapped surface is a surface both of the expansions of which, defined with respect to these null directions, are negative. So a compact orientable surface, two-dimensional surface, is called trapped or marginally trapped. If it has negative expansion or non-positive expansion for marginally trapped for both of the families. Orthogonal to S. Good. So now let us motivate our definition by considering the Kruskal. So in Kruskal spacetime, it's natural to take the two-dimensional space-like surface to be the two spheres, and the two spheres are given by the constant values of the light-line coordinates. And these things are constant. So here we can define the two null hypersurfaces given by the constant value of the coordinate u and the constant value of coordinate v. So basically the hypersurface on the union of all ingoing and outgoing, the union of all outgoing and ingoing null rays. So for each of these we can then define the normals. So du is a finally parameterized normal, and here we have the dv. And for this, the generators, again, a finally parameterized generators, are given by ddv and u2 given by ddu. Good. Now, let us compute the expansions. So, we know that the expansion is the divergence of the generator, which in this chart, so first of all, using the formula for the divergence. So and which equals to, in this chart, g mu r Good. And so, and from this formula we can compute theta 1 is then 2 to m dvr, and theta 2 is 2 er to m dur. And using the formulas from the lecture on critical coordinates, we can then find that this is the following value: 8m squared over r u, and this is minus m8 squared over r v. Now let us draw the critical diagram and see where these spheres would be trapped. So let this be the v coordinate and this be the u coordinate. So this is the singularity, this is also the singularity corresponding to white hole and the black hole, and let us S, so, and S in this diagram corresponds to a point. So for any S, we naturally define two null hypersurfaces, which correspond either to constant value of u or to the constant value of v. So in the first region, which is the exterior, we see that theta 1 is positive, while the theta 2 is negative. In the opposite asymptotically flat region, we have the opposite values. Theta 1 is negative, but theta 2 is positive. In the black hole region, and in the black hole region, we have v and u greater than 0, and therefore both expansions are negative. Therefore, any point on this diagram within the region 2 is a trapped sphere. Finally, in the white hole region, we see that both expansions are positive, which physically agrees with the definition of a white hole. All the causal curves will leave this region. All the causal curves starting in this region will leave it. So, therefore, we see that, at least for the critical space-time, indeed, the trapped surfaces lie within the black hole region. Well, does it hold in general? Yes, as we will show from the Penrose singularity theorem. Okay, so since we want to connect the presence of trapped surfaces to the formation of a central pathology, central singularity, we need to get some quantitative analysis of the expansion first. So we will derive the Raychaudhuri equation, which gives us the for which the estimation of the expansion will follow. So we want to prove the following formula, that the derivative of the expansion along the affine parameter of the null geodesic of this congruence is given by minus 1/2 theta squared minus the shear, the square of the shear, plus the square of the rotation minus the Ricci tensor term. Good. So we can, of course, good. So we are using the results from the previous lecture. So first of all, we have defined the expansion to be the trace of the corresponding transformation matrix, which can also be found as the contraction of B on the projection. So, in turn, B mu nu is the covariant derivative of the null generator, of the congruence. And finally, the dt lambda acting on scalars is the same as the covariant derivative with respect to d over d lambda, which is, in a standard chart for null geodesic congruences, is the vector field U. So, therefore, we have that d over d lambda equals to d u b mu nu b nu mu equals in turn to p nu mu, where we use that the projection is invariant under the projection P is invariant under the covariant derivative with respect to U, and we have this as U rho d nu U mu. Now, we want to commute the covariant derivative using the Cauchy formula. So this is the same as P nu mu U rho d nu d rho U mu plus the Riemann tensor rho sigma. Okay. Now, notice that the first term can be built to the total derivative, which will turn out to be 0, and the square of the covariant derivative of the U. So P nu mu. So taking U rho inside, we get d nu of d U mu, which is of course 0, because U is finally parameterized. Minus the d nu U rho d rho U mu plus the second term P nu mu Ricci mu, sorry, Riemann mu sigma rho nu U rho U sigma. Okay, so using the symmetry properties of the Riemann tensor, the contraction of the projection P is the same as the contraction of the Kronecker delta. So we get the Ricci tensor. So we get that. So we get minus Ricci tensor of rho sigma U rho U sigma minus, using the definition of B, this is the same as B rho nu, P nu mu, B mu rho. So the next step remains an exercise, but this term B rho nu, B mu rho, projection in B, can be written as B hat rho mu, B hat mu rho, and the second term. Which concludes the proof. So this statement, as you see, is purely geometric, and we haven't used any inputs from GR here. So this is correct for any geodesic concurrence. So for null geodesic concurrences, this term equals to 0, and we see that most of the terms are actually non-positive. So this term is, of course, greater or equal than 0, so in total it's non-positive, as well as this term. The only questions remain about this term, whether it's greater or equal than 0, and if we show that the second term is negative in general, then we would naturally get the formation of trapped surfaces to the future along the null geodesics of the concurrence. So in general, of course, for general geometries, this is, of course, is not correct. So we need to either assume some curvature conditions, or we need to take the input from the Einstein equations and therefore the matter. So the Einstein equations would relate the Ricci tensor to the matter, and by taking some physical conditions on the matter, such as the absence of superluminal propagation, the positivity of energy density, would likely give us the required constraints on the Ricci tensor as well. So we will see it in the next subsection, energy conditions. Okay, so energy conditions. Well, so we know the Einstein equation, which can be recast as follows, where T is the trace. And to link it to the part in the Raychaudhuri equation, we can simply assume that the right-hand side is just generally positive for any causal V. So, therefore, the most straightforward energy condition, the strong energy condition, simply states that the right-hand side, T mu nu minus 1/2 Tg mu nu, contracted on any causal vector field, is non-negative for any causal V. Yeah. So this can be interpreted, so since this equals the right-hand side, it can be interpreted that R mu nu, V nu is always positive. And since R mu nu are the second derivatives of the metric, this physically can be explained as gravity being an attractive force. So while this constraint is physical for reasonable matter, Unfortunately, it's not applicable to cosmological scenarios. So, in particular, even the presence of a positive cosmological constant, which corresponds to our cosmology, the zeta spacetime, would immediately break the strong energy condition. Similarly, the inflationary scenarios are also excluded. Therefore, we need to get some weaker conditions. So, the weak energy condition simply states that the stress energy tensor constructed on any causal V is non-negative. So for this is better, but in practice we can make it even weaker. So the null energy condition states the same thing, but only for null vectors. So for the Penrose singularity theorem, the null energy condition is sufficient. Okay, so therefore we naturally have the hierarchy of energy conditions. So we have the strong energy condition, from which follows the weak energy condition, and from weak energy condition, null energy condition follows as a special case. Now, the question is, what is the strongest but still physically relevant energy condition that we can come up with? And this energy condition is called the dominant energy condition. So the dominant energy condition is formulated by saying that the energy momentum current built from the stress energy tensor by contraction on the causal vector is a future directed it's a future directed causal vector. So the current J mu T mu nu V nu is a future directed causal vector for any time like for any future directed time like V mu. So this is the dominant energy condition. Good. Now let us consider an example of a scalar field to make sure that it satisfies the dominant energy condition. The same can be shown for all reasonable matter, including the Young-Mills field. Okay, we have the massless scalar field, and its stress energy tensor reads as g mu phi d phi minus 1/2 g mu d phi squared. So actually, it will be a good exercise to repeat this exercise, to repeat this calculation for the presence of arbitrary potential. So add the potential and find the constraints. So from the stress energy tensor, we can define the energy momentum current. T mu nu T mu nu equals minus dv phi minus dv phi d mu phi plus 1/2 of the v mu d phi squared. Good. So it is easy to see that g mu is causal. So g squared. So taking the square, g squared equals to 1/2 v squared times d phi squared, which is of course less than or equal than 0 if this is causal. So therefore g mu is causal. Now let us see that it is future directed. So we check that it is future directed by taking the scalar product with v, which we also assume future directed, and showing that it is negative. So v times g is minus dv f squared plus 1/2 v squared d f squared. So we need to constrain the bracketed term, the d phi squared. So we can then rewrite this expression as using 1/2 of the first term plus 1/2 v squared df minus dvf v squared v squared. So of course we are writing it. Here we assume that v is time-like. If v was null, then this term would vanish, and we automatically get that g is future directed. So if v is time-like, then we have this term which is definitely negative. This term is, so the first term is definitely non-positive. This term is definitely negative for time-like, and this term is space-like. So we can see that we have taken out the time-like component, and this is space-like. Therefore, it is greater or equal than 0. So in total, this is less than or equal than 0, and g is indeed future directed. Now, let us return back to the geometry. Now, we want to describe the characteristic feature of the central singularity in black holes, which is that it is the focal point for causal curves, and in particular for null geodesics. So, we have a definition. So, we will call the 2 points along the same geodesic conjugate. So, points P, Q, are called conjugate. If there exists such a deviation vector, that is the Jacobi field, so if there exists such a solution along gamma, such that it vanishes at the points P and Q, but is not zero in general. So basically, what it means is that if we have point P and point Q, and we have null geodesic going between them, so point P and Q, there is essentially a second geodesic, and in fact a one-parametric family of geodesics that link P and Q. So where this is the solution, the deviation vector S mu. And this is gamma, and this is gamma. This is gamma. So, yeah. So in certain scenarios, in particular, if you consider spacetimes with compact spatial sections, it is natural to have conjugate points. So, in particular, consider a sphere. So, consider the spacetime, which is time direction times a sphere. So, the metric is given as ds squared minus time plus metric on a 2 sphere. And we naturally have a multiplicity of geodesics linking the south pole and the north pole. So, if the set of all such points P for which the conjugate exists forms a two-dimensional surface, then the conjugate point Q is called the focal point of the surface. So, if this holds for any P in the S, surface, so that means that there exist two commuting Jacobi fields. then such point Q is the focal point. So naturally, this suggests that if we have a two-dimensional surface which has a focal point, it shrinks to it along the geodesics in the congruence defined on this two-dimensional surface. And therefore, we can expect that the expansion at the focal point would not just be negative, but in fact would be minus infinity. This is indeed the case, at least one way. In particular, we can show that if the expansion tends to minus infinity, then indeed the focal point exists. So this is in fact a theorem in Hawking analysis. That if you take null geodesic congruence, so if you take a null geodesic congruence containing all null geodesics through point P, and if the expansion tends to minus infinity at some point Q, along some null geodesic gamma within this congruence, then Q is the conjugate point to P along gamma. Conjugate point to P along gamma. And similar statement holds for focal points too. So theta minus infinity indeed means that we have a conjugate point or a focal point. Now, let us prove the following important lemma. So let us have Einstein spacetime. So the spacetime obeying Einstein equations with matter obeying null energy condition. Then the generators of the null hypersurface would obey the following constraint on the expansion. So this immediately follows from the Raychaudhuri equation. So as we recall, we had d theta d lambda equals to minus 1/2 theta squared plus sigma mu plus rotation, which was 0, which is 0 for any null hypersurface, minus the Ricci term. So this term is, of course, I'm sorry, there was minus sign here. So this term is, of course, non-negative. This term is equal to 0. And this term is positive by the null energy condition. this term is non-negative by null energy condition. So we can then bound it from above by minus 1/2 theta squared. This completes the proof. We immediately have a following corollary. So, if at some point P, the expansion is negative, and let's say it equals to the value theta 0, theta naught, so P belongs to the null geodesic, generator of a null hypersurface N, then the expansion diverges at a finite value of a finite parameter, which can be estimated as 2 over the modulo of theta naught. So the expansion diverges with infinite parameter distance of course, if null geodesic can be extended this far. Okay, so we will do the proof on the next slide. Okay, so the proof is straightforward. We simply integrate the constraint from the lemma. So let lambda equals naught at the point P. So we shift the origin of the affine parameter, and then from d lambda less than or equal minus 1/2 theta squared, it follows that d theta minus 1 d lambda is less than or equal than minus 1/2 and is greater or equal than minus 1/2. And integrating, we get that theta is less than or equal than theta naught 1 plus lambda theta naught over 2, which for negative theta naught diverges at the finite value. So okay, now we are ready. Now we only need to put one last ingredient, the causal structure, and we are ready to state and prove the Penrose singularity theorem. Now we only need to define the causal structure, and we're good to go with the theorem. So let us give some definitions. So we will define the the chronological future and the causal future of a point and of a certain subset as the set of points that can be reached from the subset by a time lake or by a causal curve. So we'll call chronological future of some subset U, where U is in some open subset of M. So the set of points reachable from U by a time-like curve, by a future-directed time-like curve. Similarly, causal future, which we denote as J plus of U, by future-directed causal curve. The past, the chronological past and the causal past are defined similarly. So if you're defining past, then it will be called I minus of U, and then it would be past directed. Similarly for the past. Okay. So let us see how it all works in Minkowski spacetime. So we have the causal cone. The causal cone, and so this is, let's say, the time, this is some x, and we have that this is the interior, and this is, so if we call this point as P, this is the interior of the light cone. And J plus is the closure. So good. Okay, now let us do a bit of definitions from topology. Now let's do a bit of definitions from topology. So first of all, what do we call an open set? So we will call a set open if for any point U there is some neighborhood which belongs to this set. So, in particular, this means that the chronological future and chronological past are open because if we slightly deform a time-like curve, because every time-like curve can be slightly deformed such that it still is a time-like curve. So this is essentially an open set. So of P and of U in general are open. So in Minkowski spacetime, J plus of P is the closure of I plus P. And we will write the closure. And we will write the closure as the bar over a set. So this, of course, holds only in Minkowski. This, of course, only Minkowski. So the closure of a set is of course closed, and therefore in Minkowski spacetime, J plus minus are closed sets. This is not true in general, because, for example, we can cut out a point from a light cone so that the G plus would be everything in the light cone except for this point, but still the closure of the interior would include the point we cut out. Okay, so let us finally define the interior. So and we can define the interior as the maximal open subset. So we'll write it as interior of U. So in particular, since I plus minus are always open, the interior of I plus minus of P is the I plus minus of P itself. P itself. So if you have an interior, then we can define a boundary. So the boundary is the closure of a set excised by interior. So let me write here. So we will write the boundary as a dot over set. And it is defined as the closure of a set minus the interior of a set. So what is the boundary? So what is the boundary of I plus in Minkowski spacetime? Well, it is the boundary of the light cone. The boundary of the light cone, which is the set of all null rays, which is the set of all future-directed null geodesics. This is true only, so in general, this is true only locally. So let us now establish some of the properties. So in Minkowski we had that the closure of I plus minus P was the causal future or past of the point P. In general, the latter belongs to the former. So So for a general spacetime, J plus minus of P is a subset of the closure of the chronological future or past. Similarly, we have that the chronological future or past is always the interior of the causal future or past. Oh, sorry, this should have been formulated for a set. I mean, in principle, for a point it's also correct, but for a set, a set is more general. So the proof of these properties can be found in Hawking-Ellis, and based on these properties, we can further derive, which is a good exercise to do, that the closure of the causal future, or respectively past, is the same as closure of the chronological future, past. And the boundary is the same as boundary of the boundary of the causal is the same as the boundary of chronological. Future or past. Now, let us do a bit more definitions. So, we will call a subset U achronal if any two points cannot be connected by a time-like curve. If no two points of U can be connected by a time-like curve. So we can then show that the boundary of the causal future or of the causal past is necessarily an achronal manifold. So we have the following theorem from Wald. Let's call this theorem 1. So we have the boundary of the causal future. We had the boundary of the causal future is an achronal submanifold of M. We will give the proof only for the achronal part only, and the proof that the boundary of J is a submanifold can be found in Wald. So how would we prove that this is anychronal? Well, we'll prove it by the contradiction. So let us have 2 points P and Q lying on the boundary, such that they are also such that one also belongs to the chronological future of the second one. So that is there is a time-like curve connecting the points. So the picture is we have some manifold U. We have the boundary J plus T, and we have the point P, and then the point Q. So this is itself the G plus U, and we have the point Q belonging to the chronological future of the point P. So yes, and this is of course the boundary of the J plus U. So we have that P Q belong to J plus U. Good. Now, since the chronological future is always open, there exists a point R around the point Q, which also belongs to the I plus of P. And R belongs to the J plus of U. Sorry, and R doesn't belong to the J plus of U. So, so we can do this because the chronological future is open, and we can find a point near the point Q, since the point Q is on the boundary, such that it is on the other side of the boundary. So it is outside the causal future. Then, since the chronological past of the point R is open, since the chronological past is in general open, there exists a point S belonging to this chronological past, such that it in fact belongs to the J plus of U. So in other words, we have constructed a causal curve from U that connects U to the point S and then to the point R, which of course is a contradiction because we assume that R lies outside of the causal future. So this shows us that our assumption was wrong. For the proof of the theorem, we need to understand more about the structure of the boundary of the causal future. So we have the following theorem, also from Wold. And this theorem says that for a closed subset, it's the boundary of its causal future is connected to U by a null geodesic, which is either past inextendable or has an endpoint on the U itself. So let U in closed. Then for any point P, belonging to the boundary of causal future, then for any point on the boundary of the chronological future, P, of course, except for the points on U itself, is connected to U by a future null geodesic. By future-directed null geodesic, gamma belonging to the G plus of U, and gamma is past inextendable or has an endpoint on U. There is an even stronger version which requires global hyperbolicity. So this one was proven in Hawking-Ellis. So let S be a compact orientable surface So since we're speaking about four-dimensional solutions, it's a two-dimensional surface. So S belongs to M, which is globally hyperbolic. S doesn't need to necessarily belong to the Cauchy surface of M. Okay, then we have that for any point P on the boundary of the chronological future of S, so that any point lies on a future-directed null geodesic starting from S, which has, so of course, orthogonal to S, which doesn't have any conjugate points, between itself and the S. So this is actually a very useful theorem for a proof. So it means that if we start from, if we specify some initial conditions on a set S, and we propagate it to the future, by future-directed null geodesics, then the boundary of the set of data, or then the boundary of the set of the space-time, which we can reach by the light, like geodesics, will have no conjugate points, except probably for the P itself. So it means that, for example, it can extend to infinity, or it can happen that it's in fact closed. So we have some point P, so we have point P prime. So these points separately are focal, are conjugate to S. Or, for example, we can have a construction if so that both paths actually connect to each other in the point P. Good. So now we are ready to formulate and prove the Penrose singularity theorem. Now we are ready to formulate the Penrose singularity theorem. So let the manifold M and G be a globally hyperbolic manifold with globally hyperbolic spacetime with a non-compact Cauchy surface. Let us further assume that the spacetime satisfies the Einstein equations and the matter satisfies the physicality condition, that is the null energy condition. So finally, assume that the spacetime M contains a trapped surface. I should probably emphasize this sigma here too. So let us immediately denote the maximum value of the expansion as theta naught. So maximum value expansion for both families of null geodesics starting from the surface T. Then the spacetime necessarily, then at least one of the geodesics is necessarily future extendable within the affine parametric, within the finite affine length. So then at least one of these geodesics is future extendable with a fine length less than or equal to over absolute value of theta naught. So where is the singularity in the singularity theorem? Well, it is in the future extensibility. So if we cannot extend a geodesic further, it means that it ends at some essential characteristic feature of the spacetime, which we can call a singularity. It can either be a curvature singularity in the classical sense of the Schwarzschild singularity, or it can be a conical singularity or other non-smoothness of spacetime. Or, alternatively, it can be something even more pathological, as the geodesics running into a Cauchy horizon. Of course, we don't want the Cauchy horizons to happen, but this is a point of a separate discussion. Now, we will prove this theorem. So, what are the inputs? We assume that the space-time is predictable in the sense of globally, in the sense of existence of the Cauchy surface and global hyperbolicity. We assume some conditions on the matter and on the space-time geometry, which we basically need to use for the Raychaudhuri equation to constrain the evolution of the expansion. And then we assume the existence of a trapped surface. Of a surface, both expansions of which are negative. And we say that this is for us sufficient to show that a singularity, that some pathology exists. Now, recall from the lemma in the section about the conjugate points. Since we have a trapped surface with negative expansion, there necessarily exists a conjugate point within some finite parametric distance from the surface T. So, lemma and its corollary. So, by the result of this lemma, we have a conjugate point within the finite affine parametric distance. This means that we have a conjugate point to the trapped surface T within the finite affine parametric distance. This means that either these geodesics actually end before, which means that they're fusion extendable and we win, or they encounter conjugate points. So assume that they indeed extend that long. That the geodesics indeed extend to conjugate points. To conjugate point that is future extendable. Causal geodesics go further than the affine parametric distance, further than the maximum affine parametric distance. Now, let us consider the boundary of the causal future of the trapped surface. Let us draw a picture. So we have two families of null geodesics emanating from the trapped surface, and recall the result of the previous section to theorem 3, which means that the null geodesics going from T, which belong to the boundary of the causal future, they must end at the conjugate point P. So we have drawn these geodesics as the boundary of the causal future of T, and it means that since there is a causal point at a affine parametric distance, these null geodesics either end at the conjugate point, or they end earlier than that. So this is conjugate point P. So either at conjugate points or end earlier. Then recall the theorem 1 from the previous subsection. The boundary of the causal future is an achronal submanifold, and the submanifold part is more important here, because submanifold means that this manifold is open and closed simultaneously, and it has no boundary. So J plus of T is a submanifold that is closed and no boundary. Okay, this necessarily complicates the picture. So, therefore, it means it cannot end, because these ends would then be a boundary. And this then means that they also cannot simply add in the conjugate points. So we may have some of the construction like this. So it can happen if we take a compact space-time, that these causal geodesics actually run around. For example, if you take a sphere or even a circle, they run around and they indeed have a conjugate point, which at the same time is not a boundary. So, a good exercise to see this is to consider the metric on a Lorentzian circle, where the angular coordinate runs from 0 to 2 pi. So, in this case, starting from any point, let's say phi equals 0, we will find that it necessarily has a conjugate point, because we can go around the circle. In our case, we are considering manifestly non-compact spacetimes, because we have stated that the Cauchy surface of the spacetime is non-compact. And the Cauchy surface, and since the spacetime is globally predictable, its topology is given by a direct product of the Cauchy surface times the time direction, which you should recall from the previous lectures. So in other words, the topology of our spacetime is manifestly non-compact as well. So we are clearly running into a contradiction, because the boundary of the causal future cannot end at it has no boundary, but at the same time it must end at the conjugate points or earlier. Now, let us make this contradiction more rigorous. And we'll do this by making our language more geometrical. And let us call this emphasizing the contradiction. So let us pick some time-like vector field. So we can always pick some globally time-like vector field because the spacetime is time-orientable. And it's time-orientable because it's globally hyperbolic. So, of course, by global hyperbolicity, the integral curves of this vector field would necessarily cross the Cauchy surface, and they would cross it exactly once. So we have integral curves of t cross sigma exactly once. Then they will intersect the boundary of the causal future, j dot plus of t, at most once, because the boundary of the causal future is an achronal manifold. So these integral curves will intersect j plus of t at most once, because j plus t is achronal. In other words, now we have a continuous injective map which connects the boundary of the causal future to Cauchy surface. Which is of course defined on the whole of the boundary of the causal future, because, well, sigma is a Cauchy surface, so there must be some curve connecting the boundary of the causal future to the Cauchy surface. So, in other words, this is now promoted to being a homeomorphism between the boundary of the causal future and its image on sigma. So, we have a homeomorphism onto its image. Sigma. Now, well, the homeomorphism means that these spaces are topologically equivalent. Now, we can bring in the contradiction, because of course the J plus T is a submanifold, so it is closed and open at the same time. So this is closed and open. Therefore, the right-hand side is also closed and open. But if it's closed, but these are, but if the right-hand side is closed and open in sigma, it must be either an empty set or the sigma itself. Well, it cannot be the empty set, of course, so it must be the whole sigma. So if closed and open in sigma, then the image of this homeomorphism is the sigma itself, which means that, and the homeomorphism is equivalent, so we can write that the boundary of the causal future of the trapped surface is sigma. This is manifestly a contradiction because sigma is non-compact, and the causal future, and the boundary of the causal future is compact by the theorem. So we have compact equivalence to non-compact. This is a contradiction. And with this, we'll conclude the proof. Now, let us do a few comments about the theorem. So first of all, the inextendability of the causal curves mean that they encounter some essential feature of the space-time. And as you recall from the previous lectures, we have defined the singularities to be not the points of the space-time. So this is why we had to use the machinery of the boundary of the space-time, because the point on the boundary does not necessarily belong to the space-time itself. And singularities are essential boundaries of the space-time. Secondly, a more conceptual feature. Yes, in the proof of this theorem, we have indeed used Einstein equations, well, together with the physicality condition of the matter, that is the null energy condition, but we used it for the Raychaudhuri equation only. Our goal was to constrain the evolution of the expansion on the congruences starting from the trapped surface. So this is easily generalizable to modified theories of gravity. Where instead it can be substituted by some more natural curvature conditions or a better suited null energy condition. So, in other words, this means that the singularity formation is an essential feature in classical theories of gravity in general. And to resolve it, we need to have a full theory of quantum gravity, which we do not have at the current moment. What about the trapped surfaces? Trapped surfaces being an invaluable tool for numerical relativists, they indeed appear regularly in numerical simulations of gravitational collapses. So Einstein equations are Cauchy stable, that is, they're stable with respect to some small perturbations of initial data, and their formation is therefore generic. Furthermore, Schoen and Yao, in 1983, they have shown that that the asymptotically flat initial data plus some sufficiently large energy density of matter would necessarily lead to formation of a trapped surface. Christodoulou pushed it even further. So in 2009, he had shown that the gravitational radiation is sufficient for formation of a trapped surface, provided that, again, it is sufficiently intensive. So, if the maximal Cauchy development contains a trapped surface, we have a singularity. That is, it's not geodesically complete. In general, if we consider non-globally hyperbolic spacetimes, so that this theorem works only on a patch of the full spacetime, it can happen that these null geodesics are not future extendable, but instead disappear behind the Cauchy horizon. This is, of course, a pathology, which means that the spacetime is not predictable, but we have discussed this feature in the previous lecture. Recall that we want to avoid such an indeterministic pathology, and we have formulated a strong cosmic censorship conjecture, which states that for generic spacetimes, the Cauchy horizon are absent from the evolution of sufficiently good data. Finally, there exist other singularity theorems. For example, there is a Hawking-Penrose theorem, which trades the geodesic, which trades the global hyperbolicity of the space-time for a much stronger energy condition, for the strong energy condition. In the next lecture, we'll consider the global properties of the space-time so that we can have some map, some diagram depicting the essential features of the space-time, the singularities, the horizons, and the asymptotic in the same picture. These diagrams are known. These diagrams are called Carter-Penrose diagrams, and we will present these diagrams for some of the known solutions. We will also finally give the definition of the black hole, which would be teleological in nature, that is, depending on the global features of the space-time. So, see you next time.